Trivedi, we lost his connection, but when he comes back, he'll be the chair. But let me give a special thanks to Steve Shenker, because he's acting as a fireman as well as a physicist today. He's Douglas Stanford was supposed to give the talk, and he had a daughter last week, and Steve was
sorry, I'm talking
for filling. Hi, Sandip. So I just was introducing Steve, but now I can pass it to you.
No, that's fine. That's fine. Okay, well, anyway, sorry about my internet snafu. Let's see if something happens. Step in, Nathan. And anyway, Steve, great to have you here. And please go ahead. I'll give you a warning at 35 minutes, if that's okay.
Okay.
All right. Excellent. Thank you.
Well, let me join the other speakers in thanking the organizers for doing a terrific job in organizing this conference in difficult circumstances, as we all know. I also want to applaud them for being willing to experiment with new formats to make this Zoom world we live in, at least for a while longer, work better. As far as my own presentation goes, as Nathan mentioned, I have to start with a caveat. I've needed to prepare this talk quite quickly. And so I'm sure I've made some physics and referencing mistakes. So if you see something, please email me, politely, hopefully. And I'll try to post a corrected version of my slides on the conference website. All right, so with that caveat, let's start. All of us know here that black hole horizons appear to display irreversible dissipative behavior. And we also know that this is in tension, or apparent tension, with the unitary quantum time evolution of the boundary theory in gauge gravity duality. And there's a simple example of this involving observables outside the horizon. It was actually pointed out, I think it's over 20 years ago, by Juan Maldacena. And that's to study the long-time behavior of two-point functions, operators far away from the black hole. A bulk semi-classical calculation of this two-point function decays indefinitely. This is the quasi-normal mode behavior. But if you do a boundary calculation, just insert a complete set of energy eigenstates, you find a double sum with matrix elements squared of e to the I times the difference of energies. These are oscillating phases. Now, we expect that black hole energy levels are discrete. The system is a finite entropy system. We're imagining finite volume and non-degenerate because black holes are chaotic. There's no special symmetries if they're non-extremal. Then at long times, this quantity should stop decreasing. It should just be the sum of these oscillating phases. It'll oscillate in an erratic way. And if it's sufficiently chaotic, the answer should be exponentially small at the entropy. And so the question one, Rafe, and we'll talk about here is what is the bulk explanation for this? And of course, this kind of tension is an aspect of the black hole information. Well, we're not going to be able to give a complete answer to that, but we've learned something in the recent years, and I'll try to summarize that. The first thing is that the main actors in this story are these oscillating phases. So let's use the simpler related diagnostic. It's called in the quantum chaos community the spectral form factor. You take out the matrix elements, you just have a double sum over the phases and some Boltzmann factor-like thing that tamps out the high energy part of the spectrum. And it's easy to see that you can write this as the product of two partition functions for each, one for each sum, analytically continued to Minkowski time. Well, one of the things that has enabled us to make progress is that to look at these very subtle phenomena is that we have simple concrete models we can look at. One such model that's played a big role is this famous SYK model. It's just an ordinary quantum mechanics of n fermions coupled together, let's say 4 at a time. And the couplings are random. They're independent, random, Gaussian distributed variables. And so this model is presented naturally, not as a given boundary system. It's a one-dimensional quantum system with just time. The bulk will be 1 + 1 dimensional, but it's an ensemble of boundary quantum systems. And we're going to often study averages in the ensemble, which we'll denote by these angle brackets. One advantage of having such a concrete, simple system is if you don't know what's going on, You can actually do computer experiments. And this is something our field doesn't have enough of, and we've been able to do that here. So a number of groups have done this. Here's a result for the spectral form factor, the function of time, and this is the spectral form factor. This is a log-log plot. And what you see is you get, at early times, you have a rapid decrease. This is the quasi-normal mode behavior, or its analog. But then at late times, you have this linearly rising ramp, as we call it, that levels off into a plateau. These are very long times, exponentially long times. And this is an exponentially small signal. Now, the slope is contained in the disconnected contribution. Just if you have separate ensemble averages of late, and it vanishes at late time, like quasi-normal mode behavior will. The ramp and the plateau are in the connected part. This is an ensemble average quantity. And these things are the signatures of random matrix eigenvalue statistics. They quantify, as we'll see a little later, long and short range eigenvalue repulsion in the spectrum. These are exponentially small effects, but they're leading at long time. Whenever you have to examine exponentially small effects, it's good to arrange a situation where they are the leading effect. So you can actually make sure they're not hidden behind something else. And one important point about random matrix eigenvalue statistics is there's a very strong belief that these are quantitatively universal in quantum chaotic systems. And we think that boundary quantum systems in ADS-CFT are quantum chaotic. So this should apply to quantum chaotic systems. And so we have to try to look for a bulk explanation of this. Well, let's imagine we try to do it in SYK. We're looking for a connected contribution. You study SYK by studying these collective fields made of fermion bilinears. Here we want something that connects the two systems. Let's call them left and right. And the link to gravity is made because at low energies, low temperatures, collective field saddles in SYK are given by bulk correlators on the bulk JT gravity geometry. So the rule is you go to 1 + 1 dimensions, you find some solution of JT gravity, and you compute the correlator of some bulk fermion field in that geometry. Well, to anticipate it a little bit, here's a wormhole geometry, a space-time wormhole. Here's a correlator connecting the left and the right side. This would give the answer for a candidate saddle for a wormhole. So we can think of G and sigma, these collective fields, as proxies for bulk degrees of freedom, since they're a way of coding geometry into correlators. It turns out that this ramp region is explained by using a geometry that we call the double cone. It's basically a piece of the eternal ADS-Schwarzschild geometry. And you identify pieces of it periodically in time because you're thinking about partition functions that are traces. So you identify this and this, the red line with the green line, the red line with the green line. And this thing, if you pull it apart, looks like has the topology of the cylinder. In JT gravity, surfaces are weighted by their Euler character. And so the weight here is either the Euler character times the ground state entropy. Cylinder has Euler character 0, so it has weight 1. That's exponentially smaller than the Euclidean black hole, which is the topology of the disk or the cigar, which has Euler character 1 and has contribution e to the s1. Two of them have contributions e to the 2s1. One important thing about this saddle point is that there's a zero mode. You can make a relative time rotation of one side with respect to the other. And so there are roughly T of these. The zero mode has that kind of volume. And that gives a linear T dependence. That explains the ramp. It turns out these are true saddles. There's a weak pressure that you can stabilize them. I won't go into this in more detail. Well, it turns out you don't have to think about SYK. You can work directly in JT gravity. So Thomas Mertens will talk about this. And it turns out JT gravity is precisely dual to another kind of ensemble of boundary Hamiltonians. You just draw the Hamiltonians from a random matrix ensemble, each is a matrix, tuned to give the leading JT gravity density of states. Because it's a random matrix ensemble, the fine-grained random matrix statistics is the same, is exact. Every random matrix potential gives the same fine-grained energy statistics. This connection to 2D gravity is formally analogous to these old matrix models of string theory. In particular, you study the 2 comma p minimal string and take the p goes to infinity limits. And this will be discussed, I hope, in Thomas's talk. But here we're taking a different perspective. It's an old one, but that the string joining and splitting, these interesting Riemann surfaces we all talk about, becomes JT baby universe, one-dimensional real universes, joining and splitting. The genus expansion parameter is e to the S naught, non-perturbative in the Newton's constant. S naught goes like 1 over G Newton. The matrix is not like an n by n Yang-Mills field. It's the full second quantized boundary Hamiltonian. It would be like the Hamiltonian of super Yang-Mills. This is effectively an e to the S by e to the S dimensional matrix. It's huge. This kind of setup where you have many baby universes is often called a third quantized setup or universe field theory. This seems to be where we are. And there are natural extensions of this idea to supergravity and the gravity coupled to gauge theories. Well, we can interpret the spectral form factor behavior as an overlap in Hilbert space. Well, in order to study thermal things in Hilbert space, you typically double the system and form, let's say, the unnormalized thermal field double state, the form that you all know. Then you time evolve on one side of the thermal field double and you form TFDT, the time evolved thermal field double. Then it's easy to see that this partition function is the overlap of the original state with the time evolved state. And the product of these two partition functions is just the modulus squared of this matrix element. Now, time evolution here is a chaotic Hamiltonian. It begins to randomize the state in the doubled Hilbert space. That's a simple rule that for random vectors in the Hilbert space of dimension d, the overlap squared goes like 1 over d. Here, d is e to the 2s. It's a doubled Hilbert space. And so this thing is of order e to the minus 2s relative to the beginning. And that is what the spectral form factor behaves like at the beginning of the ramp. The small non-zero overlap, the minimum size of the spectral form factor, is due to the finite dimensional Hilbert space we're dealing with. So here we see that wormholes provide the bulk explanation for the small non-zero overlap, indicating the finite dimensionality of the Hilbert space. And this is a recurrent theme in recent developments. It plays a central role in the replica wormhole story, for instance. Wormholes are the way the bulk tells us about this fact that you can't fit an arbitrary number of orthogonal vectors into the Hilbert space. And it increases at late time because this time evolution is not really a Haar-random unitary. And I won't elaborate on that right here. It's a side point. Well, the fact that these two left-right systems are decoupled raises a factorization puzzle. The averaged matrix element, which gives the partition function, goes to 0 at long time. The phases oscillate and there's nothing to cancel. But the squared matrix element does not. This is the wormhole contribution. Okay. So if you just imagine doing a calculation in the bulk, you'd have disk times disk. That's the decaying part. That's the slope. That's if you just squared this thing. But if you did this, you would get disk times disk plus a wormhole. And these are not the same. So the wormhole explanation of the ramp leads to a factorization puzzle if the boundary is a single quantum system, because then you'd obviously have these two things being equal. The ensemble average restores consistency because you can easily have the ensemble average of the square being different than the square of the ensemble averages. And this connection between wormholes and ensemble averaging goes back to the 80s in the work of Coleman and Giddings and Stromberg. And in this context was emphasized by Maldacena and Bauhaus. Well, we can then return to correlation functions. I won't say much about this, but I'll try to give just a brief sketch. You study the long-time thermal two-point function, and we won't normalize it. Well, you just have one boundary here, one trace. So you need geometrically to have one boundary. Well, the short time behavior will just be given by the disk, but you'll find a ramp because you have those oscillating phases. And so that has to involve some kind of wormhole. And the natural topology is a wormhole attached to the disk, sometimes called a lid geometry. So the Euler character of this is -1. So this has weight e to the minus s times a linear ramp from some almost zero mode here. And this is in fact the behavior you expect for applying the eigenstate thermalization hypothesis for those matrix elements. But there's a nice interpretation of the fact that this thing stops decaying actually because of the formation of a wormhole. You imagine a quantum created by this operator, let's say at 0 time. As you evolve in time, it falls behind the horizon. We're all used to that. That causes the exponential decay, and we're all happy with that. But then there's a small probability that you can make a tunneling kind of process that forms a wormhole. And it has amplitude e to the minus s and a factor of t because you have lots of these wormholes. And that allows the quantum to escape, get back out to the boundary. You create a baby universe. And then this operator O of t that lives close to the boundary can act on it, making a non-zero correlate. Recently, this group has been discussing more complicated multi-point correlations, in particular OTOCs, and they've developed a very nice bulk understanding that gives insights into aspects of the unitary black hole S matrix. This is a much more subtle quantity, and they've done a sharp analysis. So I want to have you look out for this paper. Talks have been given about it, but it hasn't been put on the archive yet. Well, if random matrix behavior is universal, and this is a touchstone for us, then this kind of phenomenon should apply to higher dimensional black holes as well. Kristen Jensen will talk some about this. Perhaps there's a wormhole explanation for the spectral form factor view. Well, this group, Kotler and Jensen, have found candidate higher dimensional Euclidean wormholes that might do the job. In particular, the boundary has a thermal circle as you need for the partition functions. And in fact, from a closely related point of view, you can see that this construction of this complexified double cone from eternal ADS-Schwarzschild geometry is general. And recently it's been argued that this is stable against a standard decay mechanism that people worried about, brane nucleation in these two papers. You can do other things in higher dimensions. You can imagine you have a genus 2 boundary of your wormhole in 3D gravity. Here you have a nice stable wormhole solution that was discussed in some of these earlier papers by Maldacena and Maos. Well, here's a truly terrible cartoon of what such a wormhole would look like. There's a genus 2 surface here linked by some kind of wormhole. If you make an eigenstate thermalization-like hypothesis, for the OPEs that you'd get by factorizing this on handles, the statistical CFT prediction agrees with the weight of this bulk gravitational cell. So there's some sort of fragmentary evidence that maybe 3D gravity, which doesn't have any ultraviolet problems, is dual to an ensemble of 2D CFT. Well, if that's true, what kind of ensemble would you be looking at? Well, there's some obvious instructions for this. Quantum field theories, in particular CFTs, are much more constrained than generic quantum mechanical Hamiltonians that are basically just matrices. You need locality and all kinds of other properties. We know of a few families of 1 + 1 dimensional CFTs. So people have taken a natural family, the Noreen moduli space, and averaged it and see what you get. It turns out this is consistent in the bulk with the sum over partition functions of a bulk, U1 to the nth Chern-Simons theory on different 3D geometries. You have n currents in this model, so you have to have n U1s in the bulk. And these CFTs are built from free fields. They're not chaotic. You wouldn't expect a ramp. And in fact, these people have analyzed this and you don't find a ramp. And there are other rational examples that presumably don't have ramps either. So the question is there some kind of ensemble of theories that are chaotic, the large C, large gap theories that might be the things you need? Oh, there are no candidates, at least that I know about. And so this raises the question that, because this is kind of an approximate notion of averaging, is there the notion of an ensemble of approximate CFTs? This is a question that a number of people have asked about, and I think deserves more thought. Is there some kind of notion like this running around? Well, we've been talking about the ramp surface. There's this other part of the spectral form factor called the plateau, and we need to talk about that. I say that I think our gravitational understanding of this is much less satisfactory than our understanding of the ramp in terms of wormholes. But I'll tell you some of the approaches people are taking. First, let's understand it in random matrix theory. The spectral form factor in time is essentially the Fourier transform of this density-density correlator averaged in the random matrix spectrum. Here's a random matrix spectrum. If you have an eigenvalue in E, what's the probability of finding another eigenvalue in E prime? Well, it looks like this. Here's a formula. There's a disconnected piece. It's basically the density, the leading density of states in each separate factor of the spectral form factor. This one Fourier transform gives the slope. You have a piece down by e to the minus 2s from this that goes like 1 over e minus e prime squared. Fourier transforming that says that levels don't like to be near each other at large separation, gives the ramp. But then you see this oscillating part. And the Fourier transform of this cuts off the ramp and actually turns this thing level. If you imagine going backwards, you have kind of a sharp corner here that when you Fourier transform, it gives something oscillating. And this oscillating behavior is really the smoking gun for discreteness of the spectrum in an average quantity. This, if you look at it, this means that their levels aren't right on top of each other, and these wiggles are nearest neighbor, second nearest neighbor, and so on. Well, cosine of e to the s is like e to the I e to the s. That's non-perturbative in the genus expansion. In fact, you might call it doubly non-perturbative because e to the s is non-perturbative already in 1 over g Newton, or in g Newton. And it turns out you can trace this. One way of thinking about it is to go back to the string theory analogy. You have these Riemann surfaces that define the genus expansion. Well, this kind of non-perturbative effect is a de-brane effect in a string theory where the world sheet gravity is JT. Call it the JT string. Well, so you can analyze it using techniques developed in topological and minimal string theory to analyze branes. The way this goes is you can extract this density-density correlator from this product of resolvents by looking at discontinuities here. Then, and this is the crucial step, you can relate this resolvent to the ratio of determinants if you differentiate and set this energy equal to that energy. And so you get the density-density correlator from 4 determinants, 2 upstairs and 2 downstairs. And the crucial point is that the determinant operator basically inserts a certain kind of brane. In the minimal string, it's called an FZZT brane. And the way you see that is straightforward. You write the determinant is e to the trace log. Trace in gravity means 1 boundary. E to the trace, if you expand it out, means you have no boundaries, 1 boundary, 2 boundaries, and so on. So in fact, in evaluating this, you get many disconnected geometries, many disconnected world sheets in the string theory interpretation. This is just Polchinski's calculation of de-brane effects. But here, world sheets are space-time geometries in this third quantized situation. So we have many disconnected JT space-times. Here's a picture of them. Each one of these is a little JT space-time. So it's a many universe quantum. Now, sometimes you think of universes, baby universes embedded in some mythical thing called superspace, nothing to do with supersymmetry. So in some sense, we have a de-brane in superspace, whatever that means. But you can do this calculation and find that density-density formula called a sine kernel formula. There's another approach to these non-perturbative effects that actually is the main approach that's used in the quantum chaos community that I want to just emphasize because I think it's interesting to think about. It's called a nonlinear signal model formalism, and it's really goes back to work of Efetov. And one of the other beautiful things about it is it gives the best argument, I think, that I know of why random matrix statistics are universal. It follows essentially from a symmetry category. So again, you extract rho rho from this ratio of four determinants. And then you represent the determinant here as an integral over some matter field. If you think of this Hamiltonian as having color indices, call them, then you have matter fields that are not a matrix in color space, but a vector. Now you have several matter fields, and they're labeled, let's say, by capital A, which we'll call a flavor index. You get determinants upstairs if the matter is Grassmann's, and 1 over determinant from scalars. So the system has both Grassmann's and scalars in it, and it has, in fact, a graded flavor symmetry because you have Grassmann's as well as scalars, a U2/2 flavor symmetry. These two determinants are evaluated at E, these are evaluated at E prime. So you break this nice symmetry if E is not equal to E prime. So this thing functions like a master that breaks the symmetry. Now you integrate out the color stuff. That's like integrating out gluons. You should think about this as kind of fundamental matter. And you can think about this in the bulk descriptions being created by flavor branes. So you've integrated out the color stuff and getting the dynamics on the flavor branes. You get an effective action for the meson fields in a QCD analogy that are these color singlets. And these are describe the open string dynamics on FZZT flavor branes. So the idea is a very QCD-like picture. You have quarks and glue, you integrate out the glue, you get an effective pion description of the dynamics. And just like with pions, you describe the infrared dynamics, that's E close to E prime, in terms of a nonlinear signal model with a target given by the flavor symmetry. Here it's this graded coset. The ramp is due to perturbative, I should have put quotes here, pion fluctuations around a saddle picked out by this master. The non-perturbative effects are due to another saddle. Just like in the pion Cairo-Lagrangian, you have solitons that are interpreted as baryons. Here you have another saddle, a bit like a baryon. In this context, it's called the Andreev-Altshuler instanton. And that explains the wiggles, the non-perturbative effects. And this universality of this thing only depends on having this right symmetry breaking pattern, plus a discrete symmetry that plays a role in determining this set. Now, the role of this in high energy physics in this gravity story has been emphasized recently by Altland and Sonner in a very nice paper that presents things in an accessible way. And they have a picture here of this phenomenon. Think of this as the bosonic part of the signal model manifold. There's the perturbative saddle point. Fluctuate around it, and you get the ramp. Fluctuate around it, and with this new saddle, you get this transition to the plateau. And then at very late times, corresponding to E, almost exactly the same as E prime, symmetry is restored, and the fields cover the whole sigma model. They call this causal symmetry restoration. And I raise this because the gravitational interpretation of these ideas is still an open question, and I think that deserves more thought. Further, it turns out that you can think about the plateau without all this extravagance of extra branes. Okay. The spectral form factor is really a two-boundary form. Does it inevitably require arbitrarily many boundaries to fully describe? Do you really need this many universe interpretation? Well, there's very interesting work of Okayama and Sakai that gets away without it. The trick is here, you work at fixed temperature, not energy. You don't focus on some energy. And at fixed temperature, you integrate over all energy bands. And that smooths out the ripples in this density-density correlate. The spacing changes as you change band. Then you work in the time domain, and you find in the simplest case, which is topological gravity, that the spectral form factor is just given by this explicit formula involving the error function. And it gives this nice smooth curve with no sharp feature. In fact, this thing has a convergent power series in e to the minus s naught times time. E to the minus s naught is the genus counting parameter. This looks like a genus expansion. So there should be a geometrical interpretation. And a number of us are trying to puzzle out what that means. I should point out that you can write an analogous formula for JT, and Douglas Stanford has done this. So this seems like an interesting thing to pursue, and might obviate the need for this many universe set up in this context. Well, in some sense, a really important question to address is the one that we would have thought about some years ago. The standard presentation of gauge gravity duality does not correspond to an ensemble of boundary fault systems. There's one super Yang-Mills theory. It's essentially a unique theory. And so the question is, what happens if you don't average? At present, it's too hard to examine a theory like super Yang-Mills for these very fine-grained, subtle, non-perturbative questions. So we could again look for a toy model of this non-average behavior by taking some of these simple ensemble theories like SYK or JT and look at a single member of the ensemble. Now there's a basic result. If you're in a situation, let's say, where wormholes dominate the average kind of calculations, like on the ramp, then the variance of the spectral form factor as you vary across the ensemble is of order the signal squared. There's big fluctuations. You see this by doubling the system. Here's a left-right, and here's another copy of the system, L prime, R prime. And then you fill it in with wormholes, geometries. This is just the signal squared, but there's another configuration where L is linked to R prime and L prime is linked to R. By permutation symmetry, these obviously have the same weight. Subtract off this, and you get the variance is given by this. So the variance is equal to the signal squared. This means the answer depends sensitively on the element of the ensemble. It's noisy. Okay. And this is a fundamental thing that wormholes go hand in hand with. They go hand in hand with noise. Well, here's a picture in SYK. This blue curve again is the ensemble average answer. And here, this red curve is a single sample of fermion couplings. And you can see that the slope is what we call self-averaging. It doesn't matter what member of the ensemble you have. But the ramp, there are these fluctuations. If you think about it, you can argue that the autocorrelation function in time is short. So you can think of different times as different members of the ensemble. And these fluctuations are an indication of this order 1 variance. Further, random matrix universality allows you to study this noise. And in fact, this noisy ramp should be generic in gauge gravity duality, quantum chaotic system. And it's a consequence of this kind of discrete fixed spectrum. It's erratic spectrum. It's a consequence of microstructure, the kind that was discussed in the last discussion. And so we have to ask, what accounts for the noise in the bulk discussion? There's actually an even simpler quantity to look at. Just look at one copy of the partition function. At short times, this is given by the Euclidean black hole. This is the piece of the slope. But at late times, if you just look at the formula for a given Hamiltonian, it'll oscillate erratically around 0. And the variance will grow with time. So if you square it, you'll get this linearly rising ramp. But in a single copy of the partition function, there's no generic geometric candidate for this noise. There's an important exception. In certain special cases, a fuzzball would explain something like this. But these are special. They're mostly extremal, although not always. And so in some sense, this would be a reflection of a non-extremal set of fuzzball geometries or configurations. Again, you take the modulus squared, and you get this noisy ramp. It factorizes. This is just a square of a number. But it also contains something that looks like a wormhole signal. You can get rid of the noise, let's say, by time averages. And it looks like noise and factorization puzzles are part of the same question. And the question is, how do we get a handle on that in the ball? Well, the short answer is we don't know. But there are a couple of approaches, or more than a couple, that have been explored. And here, in my final time, I'll just mention a couple of them that come up. One is to take seriously this many universe picture, going back to the work of Coleman and Giddings and Strominger in the 80s. This has been recast in the ADS-CFT context by the very interesting work by Marolf and Maxfield. See also this nice work on a paper called Eigenbranes. Here we'll follow this Marolf-Maxfield setup. The idea is you think of a many boundary Hilbert space, many copies of the boundary in the ball. You have a no boundary state, a state with one boundary, a state with two boundaries. These are boundaries in the sense of ADS-CFT, an ADS boundary. And then you have a partition function operator with one trace. You apply it to no boundary and you get one boundary. You apply it to one boundary, you get two boundaries. And you define the inner product in this Hilbert space from geometry. One boundary, which is no boundary, expectation value of partition function squared, a little like the spectral form factor, no boundary, is given by all the geometries that fill in having two boundaries. Well, there's two natural candidates. You can have a disk and a disk. That's two decoupled Euclidean black holes. Or you can have a wormhole. It's pretty clear that this quantity doesn't factorize. The expectation value in this state of z squared is not the same as the square of expectation value of z because of the wormhole. But then you can ask, are there states where things do factorize and you don't have this puzzle? And there are eigenstates of z that are called in this game the alpha states. You figure some state out where you apply z to it and you get the number back. And you can think of this state as one element of an ensemble. That's a place where you would have factorization. Well, where does the noise come from in such a description? You can think of the alpha state as written out in this way. So it's a sum of no boundary with some funny coefficient, one boundary and some funny coefficient, two boundaries and some funny coefficient, and so on. A lot of complicated numbers. Then let's say you look at the expectation value of one z in this particular state. That's like one set of fermion couplings in SYK. And then you draw geometric pictures. Well, here is the bra state with its boundaries. This is one component of it. Here's the ket state with all these boundaries. And here is the operator, the insertion. And you draw geometries here. Well, there's one geometry that just looks like this disk. And then the state boundaries are just connected together. Now, these kinds of configurations are just determining the normalization. They give alpha inner product alpha. And so this is the thing that would give the smooth decay, the smooth early time decay. But now you have other configurations where the operator boundary connects to the state boundaries. And then the state boundaries have to rearrange themselves. And you have lots of configurations like this that will depend sensitively on these numbers. And these configurations, the ones that don't have this disk here, are the noisy contribution. And because you don't have disks here, these things are down by e to the s from this. And this is a picture where the noise would come from in this kind of many universe setup. It would be coded into this complicated state in this way. Sandeep, how am I doing for time?
I lost track. I'm doing a terrible job. You're actually out of time.
I have a few more minutes.
You have 10 minutes.
I have 10 minutes.
You have, I mean, you're done with your 35 minutes. And in my reckoning, Steve has 6 minutes more. I don't know, Nathan.
Okay, I'll just go
Okay.
on and cut me off.
Yeah,
I get in trouble.
yeah.
There's
You
another.
have about.
Yeah. Okay.
Go ahead. Go ahead.
So there's another approach that my colleagues and I have been exploring recently that tries to get away from having all these many boundaries. I'm not sure we succeeded. But again, the idea is to make something minimal. The spectral form factor in Z is really a one boundary object. Can you do something more lowbrow? Well, so we retreated to where, in some sense, we started this talk, which is SYK. But now we imagine that we fix the fermion couplings once and for all. This is the kind of thing you do in a computer experiment. Now, it turns out you can formulate a collective field description, these G's and sigmas that are fermion bilinears, even when you have fixed couplings. So again, G of TT prime is described by this correlator. It codes this geometry. Now, this is only a toy model of gravity. You don't know what the bulk is really, but the great virtue of it, its saving grace, is that we have an explicit representation for the entire quote unquote gravitational pattern. That is, we can write Z as an explicit integral over this bilinear in time, this bilocal in time, this bilocal in time, of each of the items of action that depends on these fields. If we average this action, we have a simple explicit form. Even if the couplings are fixed, this is in principle calculable. You can do it numerically, say. And even if it's complicated to compute numerically, you can study its statistics. So we know a lot about what this action for fixed couplings is. And so once we have this action in these fields, in principle, we can explore all the nooks and crannies of this gravitational pattern. This is an exact rewrite, so it has to have the noise in it. Where in this integral does the noise come from? Where is it hiding? Now, in fact, we can only do a detailed analysis of this in a toy model of this toy model, where we restrict SYK to having just one time point. Okay. Then things are just ordinary integrals, and those we can poke around in. And so we can ask, where does the noise come from? Well,
really sorry to interrupt, Steve, but if you could wrap up in about a couple of minutes, it'll give time for a few questions at least, if you don't mind.
Yes, I'll wrap up in a couple of minutes. Well, a scenario in full SYK motivated by the simple model, it's not something we can derive, but it seems plausibly motivated, is that Z is given by the disk saddle, which we all expect, and that there's another saddle point in this integration space that looks like the correlators on a wormhole geometry, except all we have is the one side, the G left-left fields, if this is the left boundary. We don't have the left-right fields that you need to make a full wormhole description. And so we call this other saddle a half wormhole. And it is the source, we think, of the noisy late time behavior. In particular, it depends sensitively on which particular set of couplings you choose, whereas this contribution doesn't. And it vanishes on average. So we think this gives that, and this gives that. And these new saddle points are there in what you thought was a one boundary interval, although it seems like it's suggesting maybe there's another phantom boundary out here. But you see it in this one boundary pattern. You can then ask about wormholes. You can study Z left, Z right. The way it works is you have the ordinary wormhole, but you have other saddles, a pair of half wormholes. And this link tells you what kind of action you have. Factorization then says that this thing must be the product of these two things. At late times, the disk goes away, so you get an equation that looks like this. Wormhole plus quote unquote linked half wormholes equals unlinked half wormholes. Here you have G left right not equal 0. Here you have G left right equals 0. And here, the product of systems, there's no G left right at all. You've gone from here to here by integrating out G left right, which after all is just an auxiliary field that gives 1. So it looks like these things must be equal. They're just different ways of doing the same integral. So it looks like there's a multiplicity of bulk descriptions for the same number, depending on whether you put in a G left right kind of wormhole field or not. Well, let me conclude since my time is up. There are lots of questions always that these ideas raise. And let me just mention the big one that's in the back of everybody's mind. Are these ideas relevant for the standard holographic systems we're used to, like super Yang mills? And we don't know the answer. Fortunately, we'll have time to agonize over this. There's a discussion on these and related issues on this coming Friday at 12:20 Brasilia time, which I have to remind myself is 8:20 California. And there's also other discussions. There's, if you'd like to time travel, there's one we just had. There's one also on Friday about the black hole information problem. And there are these interesting talks that will bear directly on what we're addressing, as well as many others. So with that, let me stop, and hopefully I've left a little time for specific questions. Thank you.
Well, let's thank Steve for a great talk. Thanks a lot, Steve. We'll go right into the questions. There's a hand raised. Kumrun has his hand raised. Please go ahead, Kumrun.
Okay. Hi, Kumrun.
Hi, Steve. Thanks for a very nice review. So if you take any large N dual theory, all the integrals in that theory will give you a large N dual description in terms of Riemann surfaces, the two surfaces. In that context, SYK or the Mirzakhani model, all of those can be interpreted exactly in that same way as arising from this large N duality. So for example, this ensemble of universes you were talking about in that context becomes D branes in a Calabi threefold.
Yes.
So why should I think about the 2D as the right description of that theory, whereas I know these are just observables in a 6D theory? And is it also not the case? Doesn't this also suggest that these 2D is a very special case of dimension, that is in higher dimension, you will not have a similar statement of the ensemble, and this is very special to the large N duality and 2D?
Well, you know, you do what you can do, Kumran. We don't know what the bulk dual of super Yang mills is. None of us know what the rules in the bulk are. So we have to learn by taking simple models. And so we have to try to extract the lessons of these 2D models and see which ones might apply in higher dimensions.
No, Stephen, I'm not explaining myself clearly. I'm saying the model you're thinking is 2D is not 2D. That's my point.
I disagree with that. I think there's a way of interpreting.
The models that you are referring to can be described as topological strings in Calabi threefold. Whether you agree or not is not the point. You can describe those amplitudes as worksheet amplitudes in those gravity theories, in 60 theories.
Yes, I'm quite willing to accept that. Let's talk about that.
That's 60 theories. So talking about that theory as saying you have a 2D gravity is like saying worksheet theory is a 2D gravity, even if you're talking about type 2B in 10D.
Yes, but I think there's a way of thinking about string theories having 2D gravity. It's just a question of what you. Come on, let me finish. Let me finish my answer. The question is what you call the Calabi-Yau in the example. See, I would call the Calabi-Yau superspace. By super, I mean the space of many universes. It's certainly, there is that space there. It's a question of what you call it. So there's certainly a description of this embedding space, as there are for these minimal strings and some kind of Liouville description. But the question is, we don't want to call it space-time. We want to call it some bigger space. We want to imagine we're little ants living on the string world sheet.
Well, you can, but clearly not the right description, Steve.
Well, that's a question, whether it's the right description.
Well, it's like saying in type 2B strings, the superspace of some worksheet strings. Because 10D supergravity is what we know is the right language in the effective theory. You can describe it in terms of worksheet, that's fine. But that we know is not the right picture. That's all.
No, yes. I think I agree with everything that you said. But the question is how you use it. Then the question is, suppose we don't live in two-dimensional world sheets. Suppose we live in four-dimensional, quote unquote, world volumes. What is the analog of superspace, or do you need such an analog?
No, you won't get it. The point with that, this suggests that you're not going to get it, and that's why you're going to get difficulties on ensemble in higher dimensions. That's you're exactly going the same problems you're going to face in higher dimension is the reason that 2D works on higher you're going to have problems.
Yeah. That's why what one tries to do is what I discussed in the final part of my talk. You don't integrate over the matrices. That would be like integrating over the Yang-Mills fields. You imagine that you have fixed fields. And then you're very much like a situation in higher dimensions. How is the world sheet picture change when you don't integrate over the fields? That's like studying SYK with a fixed set of couplings, or in the work of eigenbranes, by taking one of these low-dimensional matrix string theories and don't integrate over the matrices. This is what Blumert, Mertens, and Verscheid call eigenbranes. How does that change that world sheet picture? And that would be somehow the analog of how super Yang-Mills would look. So that's precisely the goal of these kinds of analogies, is to try to draw a lesson from these simple models that we can study, but that would apply in the higher dimensional non-average. But
I think that the lessons we already know from string theory suggest that there are no higher analogs. But then yeah.
Well, Comrade, I'll ask you a question. I'll take a brief.
Or we can discuss in discussion session if we are running out of time.
Well, can you?
I was going to suggest.
Yes, okay.
Yes, sorry, Steve. Please do complete, but then let's move it on to one more question, and we'll have to close. I
don't think what I would say would be the most fruitful thing. Why don't we wait for some other questions? I'll make room for other questions.
Okay, there was one more hand raised. I think Pedro Vieira had his hand up. Pedro, did you?
I had my hand up, but I would prefer to postpone to the discussion, not to. I'll move it my questions to the discussion session. I think it's going to be a fun session.
Okay. I actually don't see any other hand up. So, Steve, maybe you can complete what you were going to say, and then we can close it. Go ahead.
I'm afraid I forgot what I wanted to say, which probably means that it's a good idea for me not to continue.
Maybe, yeah. Let me then just ask you a quick question, but feel free to postpone to discussion, which is, you said that the wormholes were in fact also related to the noise. I mean, there is this connection. And why is it that, to some extent, the wormholes represent ensemble averages, because you have multiple boundaries and multiple theories over which, and so why is it that the ensemble average is being able to calculate the noise averages?
Well, it's because you can try to compute the ensemble average of the square of something. And if you compute the ensemble average of the square of something, you know something about the variance of that thing in the ensemble.
Yes.
So it's true that you can, suppose gravity just tells you how to compute ensemble averages. Well, there's a lot of things you can compute. You can compute a quantity and its square and its cube. And so you can learn all kinds of things about the distribution of the ensemble from things you can compute from averages. And so that means gravity, if you accept it can compute everything in the ensemble, should teach you, let's say, about the variance. Now, I'll just conclude with a remark. I talked about wormholes and noise going together. You might ask a question, what happens in something like the replica wormhole story, where you have wormholes that are essentially, very closely analogous to these. The point is, in the replica wormhole story, just a second, the replica wormhole story, the boundary systems are not decoupled. There must be a faster way of doing this, but you'll forgive me here. And so what that means is that you imagine that left and right are coupled somehow. That means you don't have this permutation symmetry. That means this configuration would be different than this, because there would be, let's say, some kind of coupling, because you're tracing out over the coupled Hilbert spaces. And so the observable you're talking about couples the two entangled systems. And so then one of these would have a bigger action than the other. And it turns out that the replica wormhole saddle has the right action, the more favorable action. And that means that the noise is exponentially small in S compared to the signal. So there's a special thing about these factorizing quantities, that the noise and the signal are comparable. In the replica wormhole story, the noise isn't absent. It's just small by e to the s, or e to the minus s. And so noise is ubiquitous. And the fact that it's small in the replica wormhole story is both a feature and a bug. It's a feature in that you're pretty sure you're doing the accurate calculations. But if your interest is in the noise, it's hard to see. And there are other quantities like the black hole S matrix, where the noise will be order 1, or individual matrix elements. And so noise isn't absent, okay? It's just in certain quantities, it's not there. It's small. That was my comment.
I see. Okay. Well, thank you very much for a great talk. And let's move on to Mukund. Mukund Rangamani is our next speaker. Mukund, go ahead.